Hi everyone. In today's video we're going to be taking a look at circles a little bit more. This time we're going to be looking at different parts of circles, specifically some parts called arcs and some other parts called sectors, and then maybe some other terms will be thrown in there too that we'll learn about. But let's jump right in and take a look at first some definitions that you're going to need to know. So you can see here we got three definitions that you're going to need to know to start off with. What an arc is, what a sector is, and what a central angle is. So starting with an arc, it's pretty much just a portion of a circle. So if I look down here at this diagram, I can see that I have circle P here. Its center is P. I have this circle. And I can see that there's been 4 points labeled on that circle, J, K, L, and M. If I take any portion between two of those points, so like from J to K, that would be an arc. Or from K to L, that would be an arc. Or from K all the way around this way to J, that would also be an arc. Now there are minor arcs and there's major arcs. Minor arcs are would be an arc that's less than half of a circle. So like J to K, so arc JK would be a minor arc, arc LM would be a minor arc, arc JM would be a minor arc. A major arc is anything that's more than half of a circle. So like from K around this way through J and then to M, that would be considered a major arc. Just a side note, if it's exactly half a circle, right, because a minor arc is less than half and a major arc is more than half, an arc that's exactly half a circle is just called a semicircle, which makes sense, I suppose. But that's kind of the difference between a minor arc and a major arc. Now, when we name arcs, we use this, you can see this kind of writing down here. We'll get to some of this stuff in just a second. But you can see that the name of the arc that goes from J to M, that's a minor arc, right? The minor arc going from J to M, because of course I could go from J to M around this way and then it would be a major arc. But the minor arc from J to M is named arc JM, where we just use kind of the beginning and end points of that arc and we put this little arch over the top of those letters. So that would signify that we're talking about minor arc JM. If I wanted to name the major arc that goes from J to M, what I would do is I would use three letters. I'd use the arc that it starts with, one of these two letters that it goes through, and then the arc that it ends with. So for instance, if I wanted to name the major arc from J to M, I would maybe call it arc JLM, or I could call it arc JKM in this picture. Either one of those two things would be talking about an arc that starts at J, goes through K, and goes to M, or starts at J, goes through L, and stops at M. But if I just use two letters, it's assumed that I'm talking about the shortest arc from those two letters, so from J to M that way. So that's what arcs are. Sectors are, I think of it like it's almost like a slice of pizza or a slice of pie out of a circle. It's a figure that's formed by an arc and two radii of a circle. So for instance, if I look at arc LM here, and I look at the radius going from P to L and from P to M, if I use those three things as like the boundary, what I would be enclosing is a sector. So if I kind of colored in real quick here, this would be a sector right here, right? That portion of that circle. You know, like a big slice of pizza or a big slice of pie out of that circle. That's what we call a sector of a circle. So again, it has like three boundaries, if you will. It has an arc as one of its boundaries, and then a radius as the other two boundaries of it. A central angle is a term you're going to see used in just a few minutes here. A central angle is any angle whose vertex is the center of a circle and whose sides are radii of the circle. So for instance, again, if I look back at this picture, angle LPM right here would be one example of a central angle. It's got its vertex at the center of this circle. One side is the radius PL, the other side is the radius PM, so it fits that definition of what a central angle is. You can see a bunch of central angles in this picture. Angle LPK is a central angle. Angle KPJ is a central angle. Angle JPM is a central angle. Right? There's quite a few central angles in this picture because they all have a vertex at the center and their two sides are made of radii of this circle here. So that's some terms that we're going to need to know. Now, when we look at arcs and central angles, there's a couple things you need to know about the relationship between arcs and central angles. First of all, every arc has a measure. right? And the measure is like basically if you think of the full circle being 360 degrees, and then half of a circle being like 180 degrees, an arc has a measure like that. So if the arc is basically 1/4 of the circle, it would have a measure of 90 degrees. If the arc was 1/3 of the circle, maybe angle JPM looks like it's almost about, or arc JM here looks like it's almost about 1/3 of the circle, maybe a little bit more. Maybe arc LM is closer to 1/3. But in any case, if it was 1/3 of the circle, then it would have a measure of 120 degrees. Really what we're looking at when we want to figure out what the measure of an arc is we're going to look at the corresponding central angle that would create that arc. So if I'm looking at arc JM, and I notice that arc JM is kind of created in a way by angle JPM. Angle JPM would be the central angle that would, what we call, intercept that arc. One side of that central angle contains point J, the other side contains point M, so arc JM is intercepted by angle JPM. Whatever angle JPM's measure is, maybe it's 120 degrees, maybe it's 130 degrees, actually looks to me like it's probably close to about 160 degrees perhaps. Whatever that angle measure is, then arc JM would have that same measure. So again, if angle LPM was 120 degrees, let's say we went ahead and said that this was 120 degrees here, then arc LM would also be 120 degrees. The central angle that creates an arc has the same measure as the arc. If two central angles then are congruent, so if I look in this picture here, angle JPK and angle LPK are congruent, those two angles are congruent, then their arcs that they intercept would also be congruent. And you can see we've marked that in that picture, that arc KL and arc KJ are marked congruent with these little tick marks or these little dash marks. So that's the other idea that you need to make sure you understand. First of all, that an arc's measure is the same as the measure of the central angle that creates it. And then if two central angles are the same, then their arcs will be the same, and it works in the other order. If two arcs are the same, then their central angles will also be the same. So if we apply those ideas to this picture here, it says, what is the measure of arc AB? So arc AB, since they're just using two letters to name that, we're assuming that we're talking about the shortest arc that goes from A to B, so it would be this minor arc right here. I notice that that minor arc is created by central angle APB, right? And the measure of angle APB is 95 degrees. I know that the measure of angle APB will be the same as the measure of arc AB, so therefore I can say that the measure of arc AB would be 95 degrees. Now it also asks us for the measure of arc ACB. So that's a major arc, starting at A, passing through C before it gets to B. Right? That's what that indicates, that it starts at A, passes through C before it gets to B. What's the measure of that arc? Well, one of the ways I can figure that out is I can notice that if I started at A and went all the way around and got back to A, that would be 360 degrees, because that would be the full circle. But I'm stopping short of that. If I'm going from A through C into B, I'm stopping short of it by 95 degrees, right? We just figured out that this arc right here is 95 degrees. So if I want to find the measure of arc ACB, what I can do is I can say that arc, the measure of arc ACB, would be equal to 360 minus the measure of arc AB. So it's 360 minus 95, which is going to be 265 degrees. So that arc there would be 265 degrees. So the next thing we're going to take a look at is about finding the length of an arc. Now some people get confused about the difference between length and measure of an arc. The measure of an arc is measured in degrees, right? And it's just kind of telling you what portion of 360 we're looking at, right? It's kind of based off the idea that the full circle is 360 degrees, and so half of it would be 180 and a quarter of it would be 90. Interesting fact, we don't really know exactly why we say that a full circle is 360 degrees. It's not really been definitively proven that there's one specific reason for why we say 360 for a full circle. It is kind of odd if you think about it. maybe a full circle being 100 degrees would make a little bit more sense, because then, a 25-degree angle would just be considered 1/4, right? 25% of the full circle. But whatever the case is, the measure of an arc is just a measure of kind of comparing that portion of the arc to 360 degrees for the full circle. Length of an arc talks about, like, literally, I think of it sometimes that if I had to put a string that started at one end of the arc and laid right on top of the arc and it stopped at the other end, and then I pulled that string out straight, how long would that string be, right? How long of a string would we need to go from one end of the arc around and to the other end? That would be the length of the arc. Now, if the measure of an arc is a fraction of 360, then the length of the arc would be a fraction of the full circumference. So for instance, if my arc was a 120-degree arc, like this looks like, it's pretty close to maybe 120 degrees, then if the full circumference of my circle was 3 units, my arc length would be a third of that, because 120 degrees is a third of 360, so my arc length would be a third of the 3 units, and it would be 1 unit. If my full circumference was 30 units, then my 120-degree arc would have a length of 10 units, 1/3 of that. And the way we can kind of systematically figure out arc length is, one way we could do it is using a proportion. We could say that the arc length over the circumference, right, the ratio of the arc length over the circumference would be the same as or equal to the arc's measure over 360. And we can kind of do that. We could put a lot of times you'll see S used as the variable to represent arc length. So S over 2 pi r, because 2 pi r is our formula for circumference. Take the radius times 2 times pi. So if I make that fraction, and then I put n for arc measure over here, I could solve this proportion. Now, of course, I would need to have a number for the radius. I need to be able to put a number in for this variable, and I need to be able to put a number in for the arc measure. But if I could fill in those two numbers, I could cross multiply, and I could kind of do the math to solve for S. If I take this proportion and rearrange it to where S is by itself, I end up with this formula, because I'm going to take n over 360 multiplied by 2 pi r. Just to show you real quick why that is, right? If I take that proportion and cross multiply, I get S times 360 equals n times 2 pi r. And then if I take the 360 and I divide it here, I'll just divide it right there. And now I have S equals n over 360 times 2 pi r. Now, this multiplication and division could actually be done in any order. So I could do n times 2 pi r, do all of this, and then divide it by 360 at the end if I wanted to, if I feel like that's an easier option for me. But I can either use the proportion and cross multiply to solve, or I can use this like kind of modified version of that proportion where the arc length is just set to it, set all by itself, it's isolated, and I would just plug in the measure of the arc there and the radius of the circle there and do the math to figure out the arc length. So now let's try putting each of those formulas to use here. We're going to do this problem, and I'm going to show you how you could do it 2 ways. It says, in a circle with a radius of 4, so I have my circle that I sketched out here, I put its radius out here at 4, what is the length of an arc that has a measure of 80 degrees? So this arc here is about an 80-degree arc. And again, what I'm looking for is how long would a string, if you will, need to be so that I could lay it from this point on the circle around to this point. If I straightened this out, how long would it be? So the first thing I'm going to do is I'm going to do this using the proportion. I'm going to say that the arc length over 2 pi r is going to be equal to the arc measure over 360. And I'm going to say that would turn into S over 2 times pi times my radius of 4 is equal to 80 over 360. Then I'm going to cross multiply this. So the S is going to get multiplied by 360, and the 2 pi times 4 is going to get multiplied by 80. Now, I'm going to quickly, before I do this, I'm going to actually say, hey, 2 times pi times 4 is 8 times pi. It's going to be much easier if I leave this in terms of pi rather than grabbing my calculator and doing 8 times pi and getting an irrational number that I'd have to then round and use and kind of keep track of for the rest of this problem. So I'm just going to think of this as saying 8 pi right here. And we're going to multiply 8 pi times 80, and that's going to give me 640 pi. All I did is I multiplied the 80 times 8 and got 640. Now I'm trying to get s by itself because that's what I'm trying to solve for. So the next thing I'm going to do is divide by 360. So I'm going to say this side is divided by 360 and this side is divided by 360. And at this point, I can probably grab my calculator and type this part in my calculator. I'll take 640 times pi, 640 pi, and then I'm going to divide by 360. Just doing this on my calculator off to the side. And I'm going to get a value of s that is about, I should probably use an about symbol here, an approximate value symbol, about equal to 5.6. All right, so that arc looks like it's about 5.6, which kind of makes sense. In my sketch, it does kind of look like this. If I straighten it out, is a little bit longer than what this radius would be. Now let me show you the other way you could do that using the other version of the arc length formula that has s isolated, and we take the arc measure over 360 times 2 pi r. Let me show you that this is really going to be the same math, and it's actually probably a little bit simpler. I'll have 80 over 360 times 2 times pi times 4. And now what I can do is I can grab my calculator and I can type 80 over 360, or 80 divided by 360, get that answer, which is like 0.2 repeating, and then just say times 2 times pi times 4. So essentially, I just kind of typed all this in my calculator at once, and I still get a value, I should get the exact same answer, about 5.6. Now we're going to try this one more time with maybe a little bit more complicated picture. We can see we have 4 different radii coming out from the center of our circle. So that creates a lot of different possibilities for arcs here. It says that the radius is 6 in my picture, so let's put a 6 on any of those. I'm just going to put it on one of the radii, but I know that any of these would be 6. And it says that angle XRY is 42 degrees. So it's telling me that this is 42 degrees there, but that means that this arc up here that's intercepted by angle XRY would also be 42 degrees. And angle YRZ, this angle, is 89 degrees. So it's just short of 90 degrees. But that also means that this arc out here is 89 degrees. It wants to know the length of the arc that starts at X, goes through Y, and ends at Z. So here you can see they actually used 3 letters to describe this arc, which might make you think it's a major arc that's more than half the circle. But it's not. It just starts at X, goes to Y, or goes through Y, and ends at Z. So they're talking about this arc right here. So I noticed that that arc has a total measure of 42 plus 89, right? That the measure of arc X, Y, Z is 42 plus 89. I can add these 2 arc measures together to get this total arc that's created going from X through Y to Z. So that's going to be equal to 131 degrees. So that arc has a measure of 131. If I want to find its length, I'm going to say that its length is going to be equal to the arc measure over 360 times 2 times pi times the radius of my circle. So that's going to be 131 over 360 times 2 times pi times 6. So I'm going to grab my calculator now and I'm going to type 131 divided by 360 and then take that result and say times, I'll just say times 12 times pi, because I'm just going to go ahead and realize that if I take the 2 times the 6, I'm going to get a 12, and then that's going to get multiplied by pi. So I take my 131 over 360 times 12 pi, and I'm going to get a measure, an arc length of about 13.7.